All right, so let's first look at the bankruptcy data. Now, the bankruptcy data was a small sample, and so I had you do some resampling to just sort of like see how stable the results were and things like that. And this is what I came up with. Now, when we looked at the correlation, table, there was a lot of overlap, and we knew that's what we were doing. Is I was having you go through and look at this, and how many of you did the little correlation table where you used my little color coding script to go in and do it? Did you use any of it? A few of you used that. Let me. All right, so basically that means that you could have reduced some of the things a bit differently than I did. What I did is I went in and I found the most strongly correlated one in the group, and I started getting rid of the ones around it. And I told you in the homework, there's multiple correct ways of doing this. Now let me ask you, why if you've got 3 highly related variables and they have like 0.99 or 0.98 correlation with each other, why does it probably not matter a huge deal if you get rid of A and C instead of B, or B and C instead of A, or whatever the case may be? Why does that probably not matter a ton? Yeah. Yeah, they're so related, right? If I've got 3 pictures of the same thing and I just drop 2, I'm probably okay. If I leave all 3 in, it can confuse the modeling languages because they're trying to parcel out, and it'll say, oh, it looks the same, and so it can be problematic that way. So I dropped these, and when these are the ones that I was left with, the ones that you are left with may be slightly different, and that's no harm, no foul. This is just the way I did it, and then this is the variables that remain, okay? And then I had you go through and do some modeling both with everything in there and with just the non-collinears, just the ones that are not overlapping, okay? And then we got some results. So what was better? Was it better to have them all in there, or was it better to have just the non-overlappings in? This was not a clear, there was, sometimes it's good one way and sometimes it's good the other way. Let's talk about it and sort of like think through what's going on, okay? So if you look at these results, now I gave you this table that has these various measures in it, and then here, not long from now, we're going to spend a part of a day and just kind of learn. I've kind of like been showing you a little bit of this as we go. Let's take a minute and look at this. So recall is what proportion of the actuals did I find? So in this case, if you look up here in terms of recall, up here, with all 24 input variables, it was doing a better job of finding the true positives. Recall is, if there really is a positive in there, can I find it? What proportion of the positives do I find? And if you look up there at the top one, it was doing a pretty good job. It was finding between about 80 to 90% of the positives, the true positives, it could pick out. It was getting the positives, okay? Specificity is how good of a job is it getting the actual negatives? So in this case, by using the non-collinears, it did a much better job of being able to pick out the negatives. No, these really aren't bankruptcies. It was almost perfect in finding the non-bankruptcies. So this is kind of like the recall for negatives, and this is recall for positives. Make sure I'm not dropping this off here. Have that bouncing on my hip. There we go. Okay. Precision is what proportion of the time that I say it's a positive is it? Here it's doing better with the non-collinears. With the non-collinears, when it says it was 1, it really was. It's just not getting as many of them. Is this making sense? So recall is, if they're there, can I find them? Precision is, when I say it's a positive, is it really? And it's finding less of them, but when it says it's 1, it really is 1. And then this F1 measure is kind of an average. It's an average between recall and precision. So if we care about the true positives, and those are the main things we care about, then this is sort of a blend of those sort of things. Now when we look over here in terms of percent error, it looked like when we used all the input variables, CART was able to do a little bit better job of not having errors than it did when we had just the non-collinears. If I look up here, these tend to be consistently better, right? And then, but if I look at area under the curve, which one did better? These, right? These are consistently higher than these. And so it's kind of a mixed bag. So in general, I think what's happening is some of these ratios are more important for predicting non-bankruptcy than others. Let me state that another way. There are some categories of ratios that are important, more important than other categories. And so what looks like CART is doing is it'll use more of one ratio for the same category, like liquidity. If all liquidity ratios are important, it can use all of them. Okay? And it plucks those up in the tree and puts them up there. If we only have one liquidity ratio that we in there, it's less confusing, but it can't quite find them quite as well. So that's what seems to be happening with this particular homework problem. Yeah?
Just a quick question on your 24 variables on the random seek 0. I just got different results, but my other two lined up.
Okay. How did you guys, on when the seed is 22?
No, on the random seed equals 0.
Oh, 0. Did you guys get different numbers than I did on random seed equals 0? Maybe I biffed the split. Okay. Yeah, so I better go. Thanks for that heads up, though. I better make a note to myself. I better go redo that partition because it looks like I got a screwy one here. Okay. Okay. What's more important, error percent or area under the curve? Area under the curve seems to be more consistent. Okay. Now, if we had, what do we have, 126? We had like 100 and plus. Very small data set, so this was a teeny data set. And Dr. Keith told me about how when you guys, he gave you a challenge in class, can you do better than the professor? And you were doing your data mining. And then he told me that the way you guys did better is you just tried a bunch of different splits. And then, and then he laughed about it after class and said they were smart and they just tried a bunch of different splits and picked the one that was best and they beat me. And so next time I'm going to have to tell him you've got to use the very same partition that I do and try to beat me on the value of using your algorithms really, really well. Remember that? It might not have been your class that he did it, but basically you can see that the way you partition stuff can really matter when you've got a small set of data, right? Because a couple of different true positives being in the validation data versus being in the training data can make a big difference. Now, if you've got 10,000 records, it doesn't tend to make very much difference. But on these tiny data sets, it makes a lot of difference. So that's why I had you do some different seeds. And we were kind of looking to see what happened when we partition things differently. And so that's what's going on there. Okay. So here, this is an issue of looking at things when you've got numeric predictors that are overlapping information. Okay. In the next problem, we were really looking at categorical information that was overlapping. So basically, in the next problem, when we were looking at that, so here we were looking at all of this information where we had overlapping numerics, but in the next problem, we're looking at overlapping categories where we've got city is related to zip code, and we've got school is related to city, and we've got elementary school is in the same town as the junior high. And so if you knew one category, you could predict the others or get them within a few. So if I'm in Orem, there's only 3 high schools. If I know I've got one of those 3 high schools, I'm in Orem. So that information was really related. And I kind of led you through in the homework the thought process of how you get from 4 or 5 down to 1, excuse me. So I says, well, it shouldn't be elementary schools because there's 50 of those. And and it shouldn't be, maybe this is too specific or this is too general. And we kind of talked about, we went through that in class last time. What did you guys get? Did you find out that it was better to keep zip code or better to keep city? City, okay. So, and so basically, you get down to where you're down to a couple, and then you can empirically go figure out which one helps you with the best prediction in and of itself. Now, when I wanted to do this, is I did want to break this for you. So sometimes by doing things wrong, you learn more than by doing things right. And plus, it's fun to break things if it doesn't really hurt anything. So I want to take that data that had all that categorical information and not clean it up and run it through JUMP and watch JUMP choke on it. Okay, isn't that kind of fun? We won't really hurt anything. So in JUMP, let's take reasonably priced homes. Okay, and let's go in and run it through JUMP. And so we're going to analyze this. So we'll use our fit model, and we're going to take price, put it in our outcome variable, and take everything other than price and add it in here. Now, if I put in street address, is that going to cause a problem? If I put street address in, so my street address is 1333 North Mill Pond Drive, and yours is 250 West, 160 North, something, okay? And yours is different, yours is different, yours is different. What does it mean in the model if I put street address in? Yes. It's going to help the model at all? It's unique. It's just like saying your DNA is, one thing and my DNA is different. There's nothing systematic to help the model. There's nothing in there. So I better take that out of there, or it will not work. So let me take just street address out, because that's going to be a problem if I leave it in there. So street, you got to go, baby. So let's take that out.
On the right.
Yeah, okay. And I won't worry about the validation right now for the purpose of what I'm trying to show. Now, when I do this, because I've got all this categorical data that points at other categories, Orem is pointing at Orem zip codes. Orem zip codes are pointing at Orem. Orem's high schools are pointing at Orem. Orem is pointing at its high schools. Orem high schools are pointing to Orem's junior highs, and on it goes. So it says, warning, ill-conditioned regression problem. Don't you love these really descriptive warnings? It could have said something maybe a little nicer. It could have said something like, I can't figure it out because your input variables are related. But it's trying to help you. Okay, it's saying, I got a problem. Yeah.
I just had a question about like zip versus city. What if you pass them an XY? Would that be appropriate or no? Like latitude, longitude.
Yeah, you can pass it latitude and longitude. Those are numbers, right?
Yeah.
And so it can handle that just fine.
What's been your experience with that? Is that like too detailed, or is it better to like categorize them?
No, it actually can really matter, and here's why. If we're trying to price homes, and latitude and longitude are all the expensive homes up on the hill, as is manifest in latitude and longitude versus the inexpensive homes down here, latitude and longitude can really help a lot. It might help you more than zip code if the expensive homes and the cheap homes are in the same zip code. Does that make sense?
No, it does. That's why I was asking.
Yeah, exactly. So you kind of intuited that.
How does it clue into how rocks, like, do they treat them as a normal number, and that's how they know how close they are to each other, latitude and longitude?
Yes. Yeah.
It's a continuous variable at that point?
Yeah, it is. It's a continuous variable at that point. It's treated as a continuous instead of as a category, yeah.
Is it so normally like more, I don't know, deeper than a city? Because Provo has like 4 or 5 or 6 different.
Yeah, I mean, I would have thought that if zip code is really, now it's the if. It depends on if zip code is really specific to a consistent type of home. If it is, then zip code is probably better than city. Does that make sense? So it just sort of depends. If zip code, so for example, again, if zip code was to have, I had one zip code for student housing and one zip code for expensive housing and a different zip code for in the middle housing, then zip code's probably better than city, right? But if I've got all sorts of different houses in each zip code, then zip code's probably not going to help me that much. So it kind of depends on how systematic these categories are of what's in them. Yeah? Okay. So if I hit OK, and basically I'm saying, I know I'm breaking it, but I'm going to break it on purpose. Go do what you can do, tool. So it does it. And then it gets down here, and it says, this is biased. So I didn't clean up my Provo in all caps versus Provo leading cap. And say these are biased. Okay, so in your homework, I had you collapse these in on themselves. And then, but it makes an estimate for most of them. And then if I get down here to the bottom and say effect details, there's a bunch of this. I can't estimate this stuff. You broke me. You broke me, baby. Okay. So by giving it stuff that it can't, by giving it stuff where it can't parcel everything out, it breaks and it just says, I couldn't. Okay. So like I say, sometimes by doing it wrong, you learn more than by doing it right. And this isn't a good example of things where it just, it did what it could do, but it's signaling problems. Okay.